Alright guys, so let's try out this video thing, see how it goes. Today what we are going to talk about is deriving Kepler's equation, and we're going to use this equation quite a bit. Alright, so this is what we're going to do. And for this one, we need this picture, okay? And obviously I couldn't draw this by hand, so I did it in Illustrator. So what we have an ellipse right here. So just think about an elliptical orbit. And then we have this circle that is just circumscribed around the ellipse. Okay, and then I've got some points labeled here. We're going to use those in just a second. This is a pretty nice picture for me, guys, isn't it? I actually used a ruler and everything. So let's label some of the things on this graph, okay, and then we're going to use them to derive this equation. All right, so first thing we want to do is we're going to create a new angle, and this one is going to be capital E. Now I know we already used capital E for energy, but this capital E is going to be an angle, and this is going to be eccentric anomaly. So let's write that down here. Alright, so eccentric anomaly, that is going to be this angle right here. And you'll see what it is more later when we get to the equations. Okay, and then now we've got this point O. Alright, so point O is just the center of this circle and the ellipse. And then over at this point we've got F. So F is our focus. So remember, the focus would be like the Earth or the main planet. And then we've got an object orbiting on the ellipse. Okay, so F is going to be your main planet, or the sun, for instance. And then this point P would be the object that's orbiting on the elliptical path. Okay, so since this line right here is basically the distance between those two bodies, we've got our angle nu, so the true anomaly, that looks like that. Okay, so we've seen that one before. Alright, so now we've got those two angles going on, and then I have this distance here labeled. So this distance right here is going to equal A times sine of the eccentric anomaly. Okay, and you might wonder why it is A, which is semi-major axis, times sine of the eccentric anomaly, and it equals that because this distance between O and Q is A. Okay, so this Q point on this circle is determined by the location of the body on the ellipse. All right, so you notice from this just random point S here up to P, up to Q, it's all in just a straight line. So it's basically just measuring where our body is on that ellipse. Okay, so but this distance here is going to be A. Now we've also got the semi-minor axis, which is B, which will be right there. So again, that's just like if you want to think about the height of the ellipse. Okay, now a couple more distances. We've got this distance. So from O over to S, that is going to be A cosine capital E. And then finally from point O over to F, that will be A times E. Okay. So now we've got that. Alright, so we're going to be using these distances when we do our equation. By the way, let's label this distance from F to P. Let's call that R, which is what we've been calling it up until now anyways. So nothing new there. Okay. Alright, so we're going to come back to this picture in just a second, and we're going to color in a few things. But before we do that, let's go over the equation for an ellipse and then the equation for a circle. And I know there's shadows on here and I can't get rid of them, so hopefully they're not going to bother you guys too much. Alright, so first let's talk about an ellipse. Okay, so we know the generic equation for an ellipse is x squared over a squared plus y squared over b squared. equals 1. So if we take this equation and we solve it for y, let's call it y ellipse, that's going to equal b over a times the square root of a squared minus x squared. Okay, so now we have that. And now let's do the same thing for circle. So now we're going to have x squared over a squared plus y squared over b squared equals 1. But now here, we're going to say a equals b. Okay. So in this case, if we found the equation for y, so just solve this for y, let's call this y subscript circle. That would equal the square root of a squared minus x squared. Okay. So now what we want to do is we want to find the ratio of these two. So let's do y of the ellipse over y of the circle, and that gives you b over a. Okay, so now we have that. And we'll come back to that in just a second. Okay. So now let's move back up here. Okay. So now what I want to do is we're going to be looking at some of the sections on this picture. So let's go ahead and mark some of these off. Okay, so first let's look right here. Let's shade this in. All right, that's supposed to be a blue. I don't know why this camera won't pick up colors, but this is blue. That's what I have it in. Okay, and we're going to call that the area of PFV. All right, so we got P, we got F, we got V. So let's call that area. Okay, and another one we're going to need is this right here. All right, so that's supposed to be orange, or I have it as orange. And this one will be the area of PSF. All right, because we have P, S, and F. So it's just the area of this triangle right here. Okay. So that's what we'll call that. And then finally, I need a brighter color here. Let's see if this one will work. So now what we want is we need this whole distance here. Okay. So from PS over to V, so this whole area. I don't know if this is going to show up to you. All right, so let's finish marking this one off. Okay, so now we have that. Well, somehow the red showed up really well. Oh, that's weird. Okay, so now we have that. So that'll be area of PSV. So really that's this whole thing shaded. All right, I'm not going to put the shading in there, but that's what it would be. Okay, so now we've got these three areas. So we're going to use those three areas to find our equation. Okay, so let's go to the next page. Keep this drawing in mind. And now what we're going to do is we're going to write an equation for A, P, F, V. Right? So that's going to equal A, PSV minus A, PSF. Right? And that makes sense because if you look at this picture, PFV is this blue one, and that's got to equal area of PSV, which is this big red area, minus this orange area. Okay, so that's all we did, just subtracting areas. Now in this equation though, we can write that the area of PSV is equal to B over A times the area of QSV. Okay, so QSV, we didn't put that on here because it's a big area, but that would basically be this big area that connects those 3 points. Okay, So we can use that ratio we came up with between the ellipse and the circle, so the b over a, and multiply it by this area here, and then that'll give us the area of PSV, okay, which is this little piece here. Right, and that's just geometry, so if that part doesn't make that much sense, don't worry about too much. Okay, so now we have that. Now let's look at APSF. So this equation is going to be 1/2 times A times E minus A cosine capital E times B over A times A sine of capital E. Alright, so now we have that. So if we look at this picture again, we're going to keep going back to this picture. If we think about it, we're looking for the area right here, this orange area, this PSF. Alright, so that's basically a triangle. So the area for a triangle is 1/2 base times height. So we need to find this base, so this leg of the triangle, and then we need to find this leg of the triangle right here. Okay, so this one is easy to find. It's just the difference of AE and A cosine capital E. And then this height right here is going to be B over A times A sine E. Okay. Because that B over A, that gives you that relationship between that circle and the ellipse. Okay, so now we have that. Okay, so let's do the algebra here, kind of simplify that. So we have AB over 2 times E sine capital E minus cosine capital E times sine capital E. Alright, so that's going to be our equation for that triangular shape. So the next one will be an equation for PFV. Okay. So now if we come in here, here is this blue shape. So we'll be looking at that one. So that equation is going to be over A times A QSV minus AB over 2 times E sine capital E minus cosine E, and then sine E, where those last two E's are the capital, eccentric anomalies. Okay. So again, what that did, we look at this big QSV area again. We're going to do that ratio. So B over A and multiply by that area, and then you're going to do minus of PSF. And if you do that, you get that big PFV. Okay? Now you're not going to have to do this for the quiz or the homework or anything, so don't get too upset if it's not making much sense right now. Okay, so next one, let's do a QSV. So that is going to equal a QOV minus a QOS. So let's pull this picture back in again. Okay, so here's QOV. So we've got this shape here, and we're going to subtract this triangular shape right here, so QOS. And then that's going to give you the QSV area. Okay. So if you went through and figured all that out, you'd get 1/2 A squared times capital E minus 1/2 A cosine capital E times A sine capital E. So now that we got all that, one more, we can go back and look at APFV again. All right. So we had an equation for APFV here. It was a function of this area of QSV, Now we have this equation, so let's take this, plug it in up here. Okay. And if you do all that, I'm not going to go through all the algebra, you get AB over 2 times capital E minus E sine capital E. Okay. All right, so now we've got this. Now with this, all these equations, let's go ahead and now we're going to look at Kepler's second law. Okay. And you're going to see this part of this equation again in just a second. All right, so from Kepler's second law, we can write that T minus T0 is equal to capital T, so that's the period, over pi times AB times the area PFV. Okay. So remember, the area PFV, that's going to be the area that's been swept out since T equaled 0 right here when we passed periapsis. All right. So say this is time T at this point. This was T0. All right, so this would be the area swept out in that time. All right, so this would be an equation. And remember, your period equation is 2 pi times the square root of a cubed over mu. So now that we have this, let's go ahead and plug in what we know. So we have this equation for T, we have an equation for this area right here. So let's plug that in, and then some of the stuff's going to cancel out. Okay, let's move this up. So now, once we do that, we're going to have T minus T0 equals square root of a cubed over mu times capital E minus little e times sine of capital E. Close that parenthesis. Okay, so now we have this equation. All right, so your pi cancels from here, AB cancels from this one, and your 2's are going to cancel. So this is what you're going to be left with, right? So now remember, T0, that is the time where we pass periapsis. Okay. So now let's define a couple of things. Let's come up with a new variable, which will be capital M. And capital M is going to be equal to what's in the parentheses right here. So capital E minus eccentricities times sine of capital E. And this is known as mean anomaly. So now we have a true anomaly, we have an eccentric anomaly, and then now we have this mean anomaly. Okay, that's just what that equation is called. And then one more term, let's have n, so this is a lowercase n. Let's let that be equal to mu over a cubed. All right, and this is going to be your average angular velocity. All right, so that's what that is. So now let's rewrite our equation using these new terms. If we do that, we're going to say the mean anomaly M equals n times T minus T0, and then that's going to equal E minus eccentricity times sine of E. This equation right here is Kepler's equation. So now we've got this equation, we can get one more equation that deals with eccentric anomaly. So this next one is going to be an angle relationship between your true anomaly and your eccentric anomaly. So I'm not going to derive this one, but this is what the equation is. So we're going to have the tangent of the true anomaly over 2. that is going to equal 1 plus eccentricity over 1 minus eccentricity to the 1/2 power times tangent of the eccentric anomaly over 2. All right, so now we have that. So these two things are going to be important. All right, and you might wonder why they're important. But if you think about it, up until now, we haven't had any equations really that related the position of our orbiting object to time. So what this equation here does is it gives us time in our equation. So we could say 30 minutes into the orbit, we could, find information at that time. And we could use that to find true anomaly and some other things. All right, so that's why this equation is important, because this gives us the time that we might need to consider. Okay. So let's go to the next page. All right, so then now that we have those two equations, we'll go over examples in just a second. Let's write a few notes about it. So the mean anomaly, which was at M, that relates position and time, like I just said, for a body moving in a Keplerian orbit. All right, so we got that. And due to Kepler's second law, the mean anomaly is going to be proportional to the area swept by the focus to the body line since the last periapsis. All right, so basically you're going to be comparing your times from when you passed periapsis last. Okay. And now an important thing to note. So Kepler's equation is a transcendental equation. And if you remember, what that means is you're going to have to solve that numerically. All right, so there's no way you could solve it by hand on paper. Right? So you're going to have to use some numerical method to solve that equation. So since we must solve this numerically, we're going to go over a numerical method to do that. So this will be over Newton's method, which some of y'all have seen this already. Okay, so it's known as Newton's method. Sometimes it's Newton-Raphson method. So either term generally means the same thing. Okay, so let's go over this numerical method first, and then we'll do an example of Newton's method, just a plain math example, and then we will do an example with an orbits problem. All right, so here's what you need to know about Newton's method. And also, I should point out, since this is a numerical method, that means you're going to have MATLAB to do with these problems. Okay, so for Newton's method, what we're trying to do is we're trying to find a solution to f of x equals 0 given the differentiable function f And we also need an initial approximation P0. So basically this P0, you have to give the method a guess of where you think the solution is going to be. All right. So essentially what this does is it finds the roots of an equation. All right. So you're going to have your function and it's going to be set equal to 0. So it's going to figure out what value of x is going to make that equation equal 0. So basically you're finding the zeros or the roots of this f equation. Okay, but to do that you got to give it an initial guess. The closer your initial guess is, the quicker this method will work. All right. So let's go over our inputs we need. So we need our initial approximation, P0. We need a tolerance, so we know how accurate we want it. So let's call this TOL. In just a second I'm going to put the algorithm up here so you can see it. And then we need a max number of iterations so we don't end up stuck in an infinite loop. So let's call it N0. Then we need our function f of x. Remember, your function has to be set to 0 like we had up here. So you need to make sure it's in this form. And then we're also going to need the derivative of that function. Right? And that's why it says you have to have a differentiable function, because we're going to need the derivative. Okay. So those are our inputs. And then for the output, we need the approximate solution of P. All right, so this will be the approximation of the root. So in our algorithm, we're going to call it P. So if we can't get this solution, though, we're going to have some message that it failed. And usually you'll get that if you put in a guess that's just like totally out there. So for us, we won't have to worry about that, though. Okay, so here are our steps, and these steps will be helpful for MATLAB if you want to code up your own Newton method. So step 1, we're going to have a counter. So let's say I equals 1. Okay, so this is going to basically count how many iterations we're doing. Now, step 2, we're going to say while I is less than or equal to N0. So remember, this was the max number of iterations. So as long as we haven't reached that, we're going to do steps 3 through 6. Okay. So step 3, what we're going to do is we're going to set P equal to P0 minus F at P0 over F prime at P0. Okay. So if we think of the first time through, what we're trying to do is we're trying to get an approximation P, and to get that approximation P, we're going to use our initial guess, P0, and we're going to subtract the ratio of the function where we plug in P0 for x, and then we divide that by the derivative of the function with x equals P0. Okay. So that gives us a p-value. Now on step 4, we're going to say if the absolute value p minus p0 is less than tolerance, then basically you're done, so you want to output p. And then you want to stop the algorithm. Okay. And you want to make sure you have this absolute value in here, that way you don't have to worry about positive, negative. So you just care about the difference, you don't care about the sign. Right. So if we're below tolerance, that means we've met our accuracy requirement and we can finish. Now, if we're still greater than tolerance, that means we still have more error than we want. So I need to do another iteration. So step 5, we would set I equal to I plus 1. And then step 6, we're going to set P0 equal to P. So now our initial guess is going to be the estimate P that we just came up with. All right. So basically you'll keep doing these 4 steps right here, steps 3 through 6. You keep doing these over and over again until you reach this tolerance requirement, or until you've reached the max number of iterations. If you reach the max number of iterations, though, something is not right. So we shouldn't have to worry about that in this class with these problems that I'm going to give you. Okay? So that's step 6. And then finally, step 7 will be to output that failure message if you need to do that. Okay, and then you would stop, obviously. All right, so that's the actual algorithm for this. It's pretty straightforward and simple to do. So let's do a math example that's not related to orbital mechanics. But let's just do an example using basic equations just to go through the process here, and then we will apply it to an orbits problem. Okay. So let's see. All right, so for this example, we're going to use Newton's method to find the solution accurate to within 10 to the negative 4. All right, so 10 to the negative 4, that's going to be your tolerance. All right, and the function we're given, f of x, is going to be x cubed minus 2x squared minus f. No, that's not f, minus 5, sorry. And then f prime of x. So to get f prime of x, you just need to take the derivative of this with respect to x. So that's pretty straightforward. So we'll have 3x squared and then minus 4x. Okay. So now we have our function, we have our derivative, we have our tolerance. Next, we need to find an initial approximation. Okay. And we want to find a root that's within the range 1 to 4. Okay. So the problem didn't say that, but that's what we're going to do. Because if you notice, this is a cubic equation, so technically there are 3 roots. Right? So if you wanted to find all 3 roots, you'd have to provide 3 initial approximations. So we're only going to do 1. So we're going to look for the root that's between 1 and 4. All right, so I'm going to make our initial guess 2. Okay, so P0 is going to equal 2 because that lies between 1 and 4. All right. So now we have that. So what we're going to do is we need to calculate P. So remember, P was equal to P0 minus your function. And remember, for our function, this first time through, we're going to plug in the initial guess. We're going to plug that in everywhere we see x. Okay? So we're going to have 2 minus 2 cubed minus 2 times 2 squared minus 5 over, then do the same thing with the derivative. So we'll have 3 times 2 squared minus 4 times 2. And then that gives us 3.25. So this is our new guess for the root. Okay. So now we need to check, make sure it's within our tolerance requirements. So we're going to take this new value and we're going to subtract our old guess. And we're going to do the absolute value. So we have absolute value of 3.25 minus 2. That equals 1.25. So 1.25 is obviously greater than 10 to the negative 4. So we need to keep going. Okay, because we want this number to be smaller than this. And right now it is definitely not. All right, so to keep going, now we need to update our initial approximation. So now let's make P0 equal to 3.25. And then we just start the process over again. So now we're going to recalculate P. All right, so P is going to be 3.25 minus your function. So everywhere x is in your function, you're going to plug in 3.25, and then you're going to divide. Okay, so getting back to this, I had a phone call, sorry. So we had 3.25 minus the function when x is 3.25. We're going to divide that by the derivative and plug in x equals 3.25. All right, so we're going to do that process again. So if we do that, we get 3.25 minus 3.25 cubed minus 2 times 3.25 squared minus 5. And then we divide that by 3 times 3.25 squared minus 4 times 3.25. All right, so you're just plugging in your values. And then we need to obviously calculate the value for that. So we get 2.81104. So now we need to do the difference again. So now we're going to take this new approximation and we're going to subtract it from the 3.25 because we want the difference between these two. And remember, absolute value. So now we have this, and that equals 0.438963. Now this number is still greater than the tolerance, which was 10 to the negative 4. So that means we need to keep going and we need to update P0 again. Okay. So this next one will be iteration 3. So now we'll say P0 is equal to 2.81104. And then you do that process over again. So now we'd calculate P. So we'd have P0 minus your function f. Plug in the P0 value, divide by the derivative, and make sure you plug in that P0 value. Okay. So that's how the process is going to go. So you're going to keep doing this until you make sure the difference between your new approximation and your previous approximation is less than the tolerance. Okay, so you're going to keep going. So we're going to stop here. I'm not going to keep doing all these iterations because it has a few more. But if you went through and did them all, this is what you would get if you had a table of the initial approximation, P, and then the error. All right, so let's fill these out. So first time through, P0 was 2, P was 3.25, the error was 1.25. Okay. So obviously this was greater than tolerance, so we did another iteration. So P became P0, then we calculated P again. So I'm just going to write 2.811. The difference here was 0.439, still greater than tolerance. So P becomes P0. So put that there. And then P will be 2.698. And that error is 0.1130. So you can see your error here is going down. Still not small enough though, so we need another iteration. So now P0 for this iteration will be 2.698, and then P will be 2.6907. So you can see these values are getting closer. Sorry guys. All right, so those are getting closer, and then calculate the error. So you have 0.0073, still greater than tolerance. So one more time, So this becomes your initial approximation, so 2.6907. And then when you calculate P, you get 2.6906, and that gives you an error of 2.97 times 10 to the negative fifth. So this is within our tolerance requirement, right? Because this is smaller than 10 to the negative 4. So that means we're done, and that means that this right here is our estimate of the root that lies between 1 and 4 on the x-axis. Okay, so that would be our answer. So let's write that down. So we have 2.6906. So that's our estimate. All right. And then if you wanted to see how accurate this was, I don't have it with me because I don't have my calculator, but you could do a graph and you could check out the graph and see where it crosses the x-axis, and you could check out what value that should be. Okay, and you will find that it's pretty close to this. Okay. All right, so that's how you do Newton's method. Okay, so it's pretty straightforward. It's easy to do. It's easy to code up if you want to code up your own Newton's method. Which I will, of course, have y'all do in MATLAB, because y'all know I like that. Those MATLAB problems. Okay, so now we have this. Now we're going to go back to Kepler's equation, and we're going to figure out how to apply Newton's method to that equation. All right, so let me get a new sheet. Okay, so this will be applying Newton's method to Kepler's equation. All right, so here was our equation for the mean anomaly. So remember, mean anomaly is at capital M. So capital M is equal to eccentric anomaly minus eccentricity times sine eccentric anomaly. And we want this to be our function that we're going to use in Newton's method. But remember, for Newton's method, you have to have f of x equal to 0. So if this is going to be our f of x, we need this to equal 0, right? So we're going to move this part here over to the left. And that's going to give us m minus e plus e sine capital E. And then now this is going to be 0. And what we want to do here is we want to solve for capital E. Okay. So that means when we look at Newton's method, we can say that eccentric anomaly is going to equal your initial guess of the eccentric anomaly minus your function. And your function is made up of capital E, little e, and m. And capital E is going to equal your initial guess there. And then that's going to be divided by the derivative of your function. And the derivative is taken with respect to the eccentric anomaly. And again, we're going to plug in E0. Okay. And remember, our function is just m minus capital E plus e sine capital E. So then if we went through and took the derivative of this, we get df over de. We're going to have minus 1 from right here, plus e cosine capital E from right here. Okay, this term here goes away because it doesn't have anything to do with eccentric anomaly in that form. So now we have these two. Okay. So if we take all of this, plug it into this equation here, we get our final form. So E is going to equal E0 minus M minus E0 plus E sine E0. And we're going to put that over -1 plus E cosine E0. Okay. And here, for our initial guess, we're going to let E0 equal M. Okay. Now, this should take 3 to 4 iterations to converge. If it's not converging in 5 iterations, you've probably done something wrong. Okay, because in the most of the cases, it's going to converge in 3 to 4. All right, so now we've got that. All right, so let's do one example for this, and then we'll be done for today. Okay. And hopefully this won't take too long. Okay, so for this example, we're going to have an elliptical orbit that has a perigee radius of 9,600 kilometers, and it's got an apogee radius of 21,000 kilometers. Right. So we want to calculate the time to fly from perigee to a true anomaly of 120 degrees. Okay. So now let's draw a picture of this. So there's an ellipse, not a very good ellipse, but it'll work. All right, so it tells us the perigee radius. Let's just say here's Earth. So perigee radius would be right here. This is 9,600 kilometers. And apogee radius is over here. So it's all right, so I got interrupted again. So now we have perigee radius, and then we have our apogee radius, and our true anomaly is 120. So there's that angle right there. Right? So what we want to do is we want to find the time it takes to go from here at perigee all the way over to this point right here. So that's the time we are looking for. Okay, that's what it's asking. Right, so basically the time it takes to sweep out this area in here. Okay, so let's write down our M equation. So M is going to equal N times T minus T0, which is also equal to capital E minus E sine E. And our N equation, remember that's mu over A cubed. And we also need to find this eccentricity. So let's look for that. Okay. And we need to find A, so we can find N. So let's get those two things. So perigee radius is going to be 9,600. And we know from before that perigee radius is semi-major axis times 1 minus E. So we can solve that for A. So RP over 1 minus E is semi-major axis. Okay. Now we also have RA, which was 21,000. RA is equal to A times 1 plus E. So let's solve that equation for A. So here you get A equals RA over 1 plus E. Now both of these are semi-major axes, right? So that means that we can set these two equal to each other. And that's what we'll do next. Okay, and plug in your values for the radius. So we got 9600 over 1 minus e, and that equals 21,000 over 1 plus e. Okay. So then you'll have to cross multiply and do the algebra. Once you do that, you get 30,600 times e, and that equals 11,400. And then e is going to be 0.373. Okay. So now we know eccentricity. We'll use that in a second. Now we can take this, plug it into either one of these equations to get a. So I'm going to use the RP equation. So 9600 over 1 minus 0.373 equals 15,311 kilometers. All right, so there's A. So now we've got A, we got E, and now what we want to do is find our time. So in order to get our time, let's see, I'm trying to find a sheet here. We're going to go back to we're going to look at this equation. Okay, so here's the one with time, but we also have this equation here, if y'all remember. So we want to find E, pointing at the wrong thing here. We want to find eccentric anomaly from this equation. Right, so we already found little e. We know what true anomaly was because that was 120, it was given to us. So we can plug everything into this equation and then solve for e. Take this, plug it back up into here, and then find t. Okay, so this problem you're not going to have to do Newton's method. Okay, so let's look at that. All right, so the tangent of nu over 2 is equal to 1 plus e over 1 minus e to the 1/2 power. Tangent capital E over 2. So let's plug in our values. So we get tangent of 120 over 2 equals 1 plus 0.373 over 1 minus 0.373 to the 1/2 power times tangent of e over 2. So with this, now we can solve for e, because that's our only unknown in this equation. All right. Next page. Okay, so that gives us 1.732 equals 1.48 tangent E2. All right. So E over 2 ends up being the arc tangent of 1.17. So E then is going to be 98.96 degrees. Now this is in degrees, we need it in radians. So that's going to be 1.727 radians. So that's your eccentric anomaly, okay, at that point. So now we're almost done. Now we're going to take this eccentric anomaly and we're going to plug it into that mean anomaly equation. Which is right here. Okay, so let's take this, plug it in. Eccentricity we know, n we can find. Okay, so basically we can say square root of mu over a, which is 15,311 cubed, times t minus t0 is equal to 1.727 minus 0.373 sine 1.727. Okay. So our unknown here is this time right here. Okay, so solve for that. So your difference in time is going to be 4,078.08 seconds. So let's convert that to hours. So you get 1.13 hours. All right, so it took you 1.31 hours to go from here over to here. And that gives you this true anomaly. Okay. So that's how you can use Kepler's equation. On your homework, you'll have some like this. You'll also have some where you have to use Newton's method. Okay. So next time I'll see if I can find an example with Newton's method. I thought I had one in here, but I guess not. Okay, so that's it for today. So next time on Thursday, I'll have the next lecture up. And the next lecture will deal with Project 1. All right, so y'all got Project 1 coming up. All right, so I hope y'all have a good afternoon. Bye, guys.